When we talk about solubility, we're talking about the ability of one substance to dissolve or not into another. So if the solute, which is present in the smaller quantity, dissolves into the solvent, we say that it is soluble. Examples of this are things like salt dissolving in water, or bromine, which is soluble in methylene chloride. If they will not dissolve, then it is said to be insoluble. So an example of that is oil is insoluble in water, and this is due to having different types of intermolecular forces. So the solubility of one substance being able to dissolve into another substance, it depends on both nature's tendency towards mixing and also the types of intermolecular forces present. For review, pause the video to see if you can determine which are soluble in water and which are insoluble in water. If you said that potassium hydroxide and calcium chloride are soluble, you are correct. Potassium is always soluble no matter what it's attached to, and most chlorides are soluble, and calcium is not an exception. Silver typically is not soluble, and lead-containing compounds are also typically not soluble in water. So when we think about nature's tendency towards mixing, this is entropy. So entropy is the tendency towards chaos. So if we have two gases and we remove a barrier between them, they're going to spontaneously mix because the energy of the system becomes lower as those substances mix and become more chaotic. In order to make a solution, we also have to consider the interactions between the different components in the solution. So in order to make a solution, we have to overcome the attraction for the solvent molecules towards each other. We have to overcome the interactions and attractions for the solute molecules for each other. And that means that our solvent-solute interactions must be stronger than these individual interactions, the solvent for the solvent or the solute for the solute, in order to form our solution. In the first semester chemistry course, we talked about things being either soluble or insoluble. Really, it is more of a continuum. So when we define solubility, it's the maximum amount of solute that can be dissolved in a given amount of solvent. There's usually a limit to the amount of solubility, so if we keep adding solute, at some point it will no longer dissolve. If we talk specifically about gases, gases are always soluble in each other. If we talk about liquids, we typically refer to solubility as being miscible. So if they mix and they're mutually soluble, this is what we call miscible. So alcohol and water are miscible. Oil and water are immiscible because they do not mix. And it does change, the solubility does change depending on the temperature and the pressure. And we'll look at that a little more in depth. The chemist's general rule of thumb is like dissolves like. So if a chemical will dissolve in a solvent, it means that it has similar structure, similar intermolecular forces. So polar molecules and ionic compounds are more soluble in polar solvents, and nonpolar molecules will be more soluble in nonpolar solvents. Let's look at an example. We can categorize vitamins as either fat soluble or water soluble. And this is important because fat-soluble vitamins can build up in the human body in the fatty deposits and can become dangerous to your health or toxic if you have too much of them. Water-soluble vitamins, on the other hand, can be eliminated through urine, and so there is not much danger of them to becoming toxic. So if we think about water, water has hydrogen bonding. It is very polar, and so water is a polar molecule. If we think about fat, fat is long carbon chains, and fat is a non-polar molecule. So as we look at these different examples, we're trying to decide if the molecule is more polar and will dissolve in water or more non-polar and will dissolve in fat. Let's look at vitamin C to start. Vitamin C has lots of polar functional groups, which are alcohols. Because it has many polar functional groups, it is a polar molecule, and therefore it is water soluble. So this makes sense if we think about it because it's found in many citrus fruits and which form juices. So the vitamin C is carried into our body using a water solvent. If we look at vitamin K, we do have a couple of polar groups. So the carbon bonds and the carbon-hydrogen bonds are nonpolar. We have a couple of polar groups, but they are opposing each other. Because they're opposing each other, this makes this more overly nonpolar. So in general, over the whole molecule, it's more nonpolar, and this would be a fat-soluble vitamin. If we look at vitamin A, if we're looking for polar groups, is mostly carbon and hydrogen. We only have one polar alcohol group. So overall, the whole molecule is going to be nonpolar or fat soluble. If we look at vitamin B, so we've got alcohol groups. We have a acid group, a carboxylic acid group. There is also an amino group, or an amide. I apologize, because we've got the carbon double bonded oxygen. So these are quite polar groups. And so this is going to be a polar molecule and water soluble. Here's a practice for you. Determine whether each compound is soluble in hexane. Pause the video to determine your results. Hexane. Hex means that there are 6 carbons. Ane means they are all singly bonded. So we have 6 carbons, no functional groups. So this is going to be a very nonpolar molecule. So if we are going to have something to be soluble in it, it is going to have to be nonpolar itself. So water is polar. So no, it will not be soluble in hexane. If we look at ammonia, ammonia is polar. Look at its structure. It is not symmetrical, it's asymmetrical, so it makes it polar, which means no, it will not dissolve in hexane. If we look at propane, propane is a carbon chain with 3 carbons, no functional groups, so this is going to be nonpolar. So yes, it will dissolve in hexane. Hydrogen chloride, the chlorine is more electronegative, It's going to pull the electrons towards it. This is a polar molecule. So no, it will not dissolve in hexane.